Welcome to Pre-Cal Notes 1-2, New Functions and Their Graphs. In this lesson, we're going to look at two new functions that are very well suited to our study of transformations in graphing. Then we'll learn one new transformation. The first function we're going to learn is the greatest integer function. The notation looks like absolute value bars, but with feet. This is also known as the floor function, or the step function. We'll see why later. The definition is that floor of x is the greatest integer that is less than or equal to x. For example, the greatest integer that is less than or equal to 5.78 is just 5. Pause the video for a moment and try these examples. Make sure you understand. Okay, here are your answers. The greatest integer less than or equal to 0.12 is just 0. Pi is a little bit over 3. The greatest integer less than or equal to pi is 3. The greatest integer that is less than or equal to 12 is 12. Watch out for the negative numbers. Floor of negative 7.4 is negative 8. That is less than or equal to x. We're not just chopping off the decimal. We're looking at what's less than negative 7.4. Similarly, with negative 0.01, we have negative 1. Let's take a moment and see what this graph is going to look like. We're going to come up with a table of values and see where it takes us. We know that floor of 0 is 0. So there's 0, 0. We know that floor of 0.5 is also 0. The greatest integer less than 0.5 or equal to 0.5 is 0. In fact, we can get as close as we want to x equals 1, and the y value will still be 0. We indicate this with an open circle at 1. We can get arbitrarily close to 1, but if x is 1, suddenly y is 1. Similarly, if we look at some negative numbers, negative 1, negative 1, negative 0.5 gives us negative 1. And again, we can get as close to 0 as we can. And the floor of that number is still going to be negative 1. Y is negative 1 all the way up to, but not including 0. We can throw in a couple of random values here. And see that the same thing is happening near 2. We're going to get up to, but not including 2, because the floor of 2 is 2. I think this is enough to see the pattern. What we get is a stair-step effect. And this is why this is sometimes called the step function, because of its graph. Naturally, when we come across new functions, we ask what the domain and range are. Well, clearly, we can input any real number and get an output. The domain is all real numbers. The range is more interesting. The y values are all integers, so we don't have the set of all real numbers, we have the set of all integers. We indicate that with a double bar z. The second function we're going to look at is the Signum function. This is also known as the sine function. This function's output will simply give an indication of whether x is positive, negative, or 0. The output will be 1, 0, or negative 1, depending on the sign of x. For example, signum of 3.8 is 1. It is a positive number, and so signum returns a 1. Pause the video and try these examples. Here are your answers. Signum of negative 0.01 is negative 1. It is a negative number. Pi is a positive number. For the next three examples, I included some greatest integer functions. So the floor of 0.9 is 0. This is the same as taking signum of 0. The answer is 0. And now we finally have the greatest integer less than or equal to signum of 0.5. Well, signum of 0.5 is 1. That is a positive number. The greatest integer less than or equal to 1 is 1. Let's take a look at how this graph is formed. Clearly, 0 has an output of 0. 1 has an output of 1. 2 has an output of 1. In fact, every positive x has an output of 1. So what we're going to get is a horizontal line to the right. And this works for every positive number, so we can get as close to 0 as we want. The output will still be 1 until we actually get to 0. We indicate this with an open circle. For negative numbers, same kind of thing happens. Any negative number will have an output of negative 1. Our domain, of course, is all real numbers, because every real number is either positive, negative, or 0. The range is more interesting. There are only 3 possible values. We indicate this with formal set notation. On the next page, you have some graphs for reference. We're going to look at how to do transformations. The first thing we're going to do is identify A, B, C, and D. Pause the video and try to pick out A, B, C, and D, and indicate what their effects are going to be. Here are the values. Note that C is positive 1, and D is 0 because there is no D parameter. These correspond to the following effects. Remember that B is a compression parameter. If B were 4, then it would be a compression. Since it's fractional, it is an expansion. This graph is going to expand to 4 times its normal width. Like I did in the last notes, I'm going to plot this function with only the shifts applied. I'm going to do this in gray. This is something that you would want to do just in very light pencil. We're going to use this as a basis for for applying our stretches. Now, when we stretch from our new origin, our expansion is times 4. So here's our starting point. We go 1, 2, 3, 4. Our vertical stretch has a factor of 3, but we also flip it. So instead of going up 1 and right 1 to the next stair step, we go right 4 because of the expansion and down 3, so it's flipped and vertically expanded. We can now take the stair step pattern and extend it back to the end of the grid. There it is. Next, we'll plot a graph of a Signum function. Now, as for this hint, what effect does the B parameter have on the Signum graph? Well, remember that the B parameter is a horizontal compression. If we look back at the Signum function, if we stretch or compress this horizontally, it's not going to matter because we keep the same y value on each ray. So while we will identify the B parameter, it's not going to affect our graph in the slightest. Make sure you catch that c is negative 3. It's x minus c. And here are the effects. Once again, I'm just going to apply the shifts and draw a very light colored indication of what the function would look like unstretched. And a normal Signum function is going to have this pattern. But when we apply the stretches, we have no flips. We're going to stretch it vertically by a factor of 2. And again, our horizontal compression doesn't do anything. Finally, we look at our last transformation. This is an absolute value transformation. We're going to take a function like this and put absolute value signs over it. For example, when we look at number 7, we're going to have some elements of a parabola, but the absolute value is going to change it slightly. So first, notice that this is an output transformation. An output transformation always affects the y-coordinate. So every negative y value is going to be plotted as a positive number. Here's our how-to. We're going to start by ignoring the absolute value signs. I'm going to draw this very lightly, and you can too in pencil. Just make sure I know that this isn't your final answer yet. X squared minus 2 is simply a parabola that's been downshifted by 2 units. So our parent function really is x squared. Now, to get the final product, everything above the x-axis is going to stay. Everything below the x-axis is going to flip to be positive. This negative 2 is going to flip to positive 2. This negative 1 flips to positive 1. And we connect with the same curve, only above the line. Similarly, in our last example, we're going to identify the parent function. That's really what's inside the outer absolute value transformation. So we're going to base this on an absolute value function. We start by ignoring the outermost absolute value. Now, when we apply the absolute value transformation, we keep everything that's above the x-axis, and we bounce everything that's below the x-axis.